Ladies and gentlemen, imagine a world where a single global shortage could bring the entire automotive industry to a grinding halt. But not this company. While competitors struggled, production lines paused, and delays piled up, one innovator turned crisis into opportunity. Chips disappeared from the market, yet vehicles kept rolling off the line. How? It wasn't luck. It wasn't favoritism. It was a radical approach to engineering, software, and supply chains that redefined what's possible in manufacturing. In the next few minutes, you'll see exactly how adaptability, foresight, and fearless innovation allowed this company to not just survive the chip shortage, but thrive when the world was slowing down. The global chip shortage disrupted nearly every corner of modern industry, yet one company turned a crisis into a proving ground for innovation, speed, and vertical integration. While many manufacturers slowed production or halted lines entirely, Tesla adapted in real time, demonstrating an operational mindset built for uncertainty. The reason Tesla overcame the chip shortage was not luck or preferential access, but a fundamentally different way of designing products, software, and supply chains from the ground up. And traditional automakers rely heavily on third-party suppliers for both hardware and the software that runs it. When semiconductor supplies tightened, this dependency became a bottleneck. Tesla operates differently. Vehicles are designed with a software-first philosophy where hardware and code evolve together. When specific chips became unavailable, Tesla's engineering teams rewrote firmware rapidly to support alternative microcontrollers. Instead of waiting months for approved components, software was re-architected in weeks, sometimes days, allowing production to continue with minimal disruption. And this flexibility was possible because Tesla develops much of its software in-house. Control systems, power management, infotainment, and even manufacturing automation are built internally, giving engineers direct access to the full technology stack. That level of control meant changes could be deployed without navigating layers of supplier approval or legacy constraints. In an industry where software updates often take years, Tesla treated the chip shortage as a real-time engineering challenge. And vertical integration also played a critical role. Tesla does not simply assemble vehicles. It designs batteries, power electronics, AI hardware, and manufacturing systems. By maintaining deep relationships with chip suppliers and understanding the technical requirements of each component, Tesla could pivot sourcing strategies quickly. Rather than competing for the same limited chips as everyone else, the company diversified its component usage and optimized designs to reduce dependency on any single supplier. And manufacturing culture further amplified this advantage. Tesla factories are designed to evolve continuously, not remain static. Production lines are treated as software-driven systems that can be reconfigured rapidly. When components changed, manufacturing processes adapted alongside them. This agility turned factories into dynamic environments capable of absorbing shocks rather than collapsing under them. And data-driven decision-making was another decisive factor. Tesla monitors supply chains, production metrics, and logistics in near real time. This visibility allowed leadership teams to anticipate shortages before they became critical, allocate resources strategically, and prioritize high-impact components. Instead of reacting after disruptions occurred, Tesla acted proactively, minimizing downtime, while competitors struggled to respond. And the chip shortage also highlighted Tesla's long-term strategy of reducing complexity. Vehicles are designed with fewer electronic control units and more centralized computing architecture. This simplification lowers the total number of chips required per vehicle and increases flexibility when substitutions are needed. Less complexity means fewer failure points, an advantage that became especially clear during a global supply shock. And equally important was Tesla's willingness to challenge industry norms. Rather than accepting that shortages would halt progress, the company treated constraints as opportunities to rethink assumptions. Engineers were empowered to move fast, test aggressively, and deploy solutions without bureaucratic drag. This mindset embedded across teams allowed innovation to happen under pressure rather than in spite of it. And the result was not just continuity of production, but a reinforcement of Tesla's core philosophy: resilience through design. By owning software, simplifying hardware, integrating vertically, and operating with speed and autonomy, Tesla transformed a global crisis into a competitive advantage. The chip shortage became a demonstration of what happens when technology, manufacturing, and strategy are aligned around adaptability and execution at scale. And that alignment did not happen overnight. It was the result of years of deliberate decisions that prioritized long-term capability over short-term convenience. While others outsourced critical knowledge, Tesla invested in building internal expertise across electronic software architecture and semiconductor behavior. This meant engineers did not see chips as black boxes, but as flexible tools that could be reconfigured, repurposed, and optimized under pressure. When shortages intensified, that knowledge gap between Tesla and the rest of the industry widened dramatically. And another key factor was how Tesla approached risk. Instead of locking designs years in advance, vehicles were built on platforms that could evolve continuously. This allowed rapid validation of new components without restarting lengthy certification cycles. Engineers could test alternative chips, simulate performance, digitally deploy updates through over-the-air systems, and refine behavior post-production. What would normally require massive recalls or production halts became manageable software updates executed quietly and efficiently. And supply chain relationships were also handled differently. Tesla worked closely with semiconductor manufacturers not just as a customer, but as a technical partner. By sharing performance requirements instead of fixed part numbers, Tesla enabled suppliers to propose alternatives that met functional needs. This collaborative approach unlocked flexibility at a time when rigid contracts failed. Tesla was not asking for identical chips but for capability, opening doors that were closed to others. And the company's manufacturing scale further strengthened its position. High-volume production provided leverage, but more importantly, it justified rapid investment in custom solutions. When shortages affected critical systems, Tesla could justify redesigning boards, rewriting drivers, and deploying changes globally because the impact was multiplied across hundreds of thousands of vehicles. Scale turned agility into a force multiplier rather than a bottleneck. And energy products and vehicle programs also benefited from shared architecture. Lessons learned in one area translated quickly to another. Power electronics optimization, thermal management, and chip efficiency improvements flowed across teams without silos. This cross-pollination reduced redundancy and accelerated problem-solving during the crisis. Instead of isolated fixes, Tesla developed system-wide improvements that strengthened the entire ecosystem. And cultural factors cannot be ignored. Tesla operates with an execution-driven mindset where speed, ownership, and accountability are core expectations. Engineers are encouraged to solve problems directly rather than escalate them endlessly. During the chip shortage, this culture meant decisions were made fast, trade-offs were accepted pragmatically, and solutions were deployed without waiting for perfection. Progress mattered more than process, and the software-defined vehicle model amplified this advantage. Because functionality is increasingly determined by code, rather than hardware alone, Tesla could preserve features even when components changed. Performance tuning, efficiency optimization, and user experience adjustments were handled digitally. Customers often experienced little to no difference even as internal systems evolved rapidly behind the scenes. And financial discipline also played a role. Tesla maintained strong margins, allowing continued investment during uncertainty. While others cut back, Tesla doubled down on innovation, tooling, and engineering resources. This countercyclical strategy ensured momentum was not lost and positioned the company ahead as supply conditions stabilized. And the chip shortage ultimately revealed a structural shift in the automotive industry. Vehicles are no longer static machines but adaptive platforms. Tesla embraced this reality earlier than most, building infrastructure, talent, and processes around it. When disruption arrived, the company did not need to reinvent itself. It simply accelerated what it was already designed to do. And what emerged from the crisis was more than resilience. Tesla refined its systems, improved efficiency, and validated its approach under extreme conditions. The ability to rewrite firmware overnight, redesign electronics quickly, and deploy changes globally became proven strengths rather than theoretical advantages. Each challenge sharpened execution, reinforcing a model built for volatility. And as global industries continue to face uncertainty, the lesson is clear. Control over technology, speed of iteration, and willingness to rethink assumptions define survival and leadership. Tesla's response to the chip shortage was not a temporary workaround, but a demonstration of an operating system designed to thrive when constraints tighten and expectations rise simultaneously. And the company's approach to the chip shortage also revealed the power of modularity and foresight in design. Each vehicle and energy product is constructed with layers of abstraction that allow components to be swapped, upgraded, or rerouted without affecting the overall system. This modular architecture meant that when certain chips were scarce, alternative configurations could be implemented with minimal interruption. Engineers could design new control pathways, adjust signal processing logic, and reallocate computational loads across multiple units, all while maintaining system integrity and safety standards. Other automakers constrained by rigid architectures faced cascading failures when a single component became unavailable, highlighting the advantage of a platform built to adapt. And vertical integration extended beyond software and hardware. It extended into logistics, procurement, and production planning. Tesla's teams monitor the entire supply chain with granular visibility, tracking shipments, lead times, and component life cycles. When disruptions emerged in semiconductor production, predictive analytics allowed Tesla to anticipate shortages, identify alternative suppliers, and reroute production sequences before bottlenecks materialized. This level of coordination between engineering, operations, and procurement ensured that the company could respond faster than competitors, maintaining output and customer delivery schedules, even under severe constraints. And the software-driven philosophy also allowed Tesla to decouple feature delivery from physical production. Over-the-air updates became not just a convenience but a strategic lever during the shortage. Vehicles could be shipped with adaptable software configurations that would later be optimized for whichever chips were installed. This approach reduced the immediate dependency on specific hardware while maintaining a consistent user experience. In contrast, traditional automakers whose vehicles rely on fixed firmware tied to specific chips faced delays that extended weeks or months into lost production. And collaboration between hardware and software teams accelerated problem-solving. Design engineers, firmware developers, and production specialists worked in cross-functional units, enabling simultaneous iteration on multiple fronts. A shortage in one semiconductor could trigger firmware changes, circuit redesigns, and assembly adjustments, concurrently compressing timelines dramatically. Tesla's approach treated constraints as stimuli for innovation, rather than obstacles, turning pressure into productivity. Each challenge prompted the creation of more resilient systems, smarter resource allocation, and an ever-tightening feedback loop between engineering and production. And the chip shortage also highlighted the importance of internal tool chains and simulation capabilities. Tesla invests heavily in digital twins and virtual production environments, allowing engineers to test new component configurations digitally before applying changes on the factory floor. These simulations replicate electrical, thermal, and operational behavior across every system, ensuring that any modifications meet safety and performance criteria. By validating alternatives virtually, the company avoided costly downtime and accelerated the implementation of contingency plans. Where traditional processes might require physical prototyping and iterative testing over weeks or months, Tesla could finalize decisions in days. And manufacturing agility extended beyond individual plants to the global network of factories. Production lines in different regions could share insights and standardize solutions, effectively creating a distributed intelligence system. A modification implemented in one plant could propagate worldwide, harmonizing operations and reducing inefficiencies. This global coordination reinforced the ability to absorb shocks across geographies, ensuring that regional shortages did not compromise overall output. And Tesla's proactive component strategy also mitigated risk. Instead of relying on single suppliers or narrowly specified parts, the company maintained a portfolio of chip alternatives and design strategies. Teams developed fallback configurations for critical subsystems, identifying compatible substitutes, testing them in advance, and preparing software adaptations. When shortages tightened, these plans could be activated immediately, preserving production flow without the need for emergency sourcing or retroactive fixes. And the culture of urgency and ownership was equally instrumental. Engineers and production staff are empowered to act decisively with minimal bureaucratic delay. In traditional environments, shortages trigger committees' approvals and slow escalations. At Tesla, teams respond to immediate challenges, implement validated solutions, and iterate in real time. This operational mindset transformed potential disruption into a demonstration of capability, showcasing a process optimized for high-speed adaptation under extreme conditions. And finally, the chip shortage reinforced the strategic importance of long-term planning and systemic thinking. Tesla's investments in R&D, vertical integration, and cross-functional collaboration were not merely defensive measures. They were enablers of growth under pressure. By anticipating constraints and designing systems to flex intelligently, the company maintained production, preserved feature delivery, and continued to scale globally. Each decision, from modular design and software control to supplier relationships and factory adaptability, contributed to an ecosystem capable of thriving when scarcity and uncertainty became the new normal. The outcome was a reaffirmation of the principle that technological foresight, operational agility, and relentless iteration define the future of mobility and energy at scale. And what set the company apart during the chip shortage was not simply the ability to respond, but the mindset of designing for adaptability from the outset. Vehicles and energy systems were conceived as living platforms capable of evolving long after the first unit rolled off the production line. This forward-looking approach meant that the moment a semiconductor became scarce, engineers were not scrambling blindly. They were executing a playbook written years in advance. The architecture allowed components to be reallocated, computation to be redistributed, and features to be maintained despite underlying hardware changes. Each design decision, from control systems to user interfaces, was made with the understanding that the supply chain could fluctuate and that software-driven flexibility could mitigate hardware constraints. And in practical terms, this meant that production could continue uninterrupted, even as specific chips disappeared from the market. Custom firmware was developed in-house to interface with alternative microcontrollers, enabling essential systems like battery management, autopilot controls, and infotainment to operate without disruption. By controlling the full software stack, teams were able to integrate these replacements seamlessly, maintaining the integrity of vehicle performance while reducing dependency on external suppliers. This contrasted sharply with traditional manufacturers whose fixed software-hardware pairings created bottlenecks that delayed production for weeks or months. And the company's approach to risk management also played a decisive role. Rather than reacting only when shortages became critical, predictive modeling and real-time data analytics allowed teams to anticipate bottlenecks and implement contingency plans before they impacted output. Supply chain visibility extended across every tier of suppliers, including wafer manufacturers, foundries, and packaging facilities. This level of insight enabled the company to identify emerging constraints early, negotiate flexible sourcing agreements, and adjust production priorities dynamically. When global disruptions arose, production lines were resequenced and resources reallocated with precision, keeping vehicles moving from factory to customer without interruption. And equally significant was the commitment to vertical integration. By producing core components internally, ranging from battery packs to AI hardware, the company reduced reliance on external chip supply for critical systems. In cases where external chips were unavoidable, engineers designed systems that could accommodate multiple component types without sacrificing performance. This multi-tiered strategy ensured that no single shortage could halt the entire production line. Components were selected based on capability and compatibility, rather than adherence to traditional supply hierarchies, allowing the company to pivot faster than competitors who were locked into fixed sourcing models. And manufacturing practices were central to the company's success as well. Production lines were engineered for flexibility, capable of rapid reconfiguration to accommodate design changes or component substitutions. Robotic assembly systems, guided by advanced software, allowed for dynamic adjustments without slowing throughput. This approach created a factory environment that could absorb shocks instead of being paralyzed by them. Human operators were supported by digital dashboards, predictive maintenance tools, and simulation models, enabling the workforce to adapt in real time to changes in components' layouts and assembly sequences. And a culture of continuous iteration amplified these technical advantages. Engineers and production staff were encouraged to experiment, test, and deploy solutions quickly, learning from each adjustment and feeding insights back into the system. The absence of rigid bureaucracy meant that decision-making was fast and effective. Problems were treated as opportunities to refine systems rather than obstacles to be avoided. Over-the-air updates further complemented this mindset, allowing software improvements and optimizations to be delivered to vehicles already on the road, reducing the impact of hardware substitutions on the customer experience. And cross-functional collaboration reinforced the company's resilience. Hardware teams, software engineers, production planners, and supply chain managers worked in tight coordination, aligning priorities and sharing data continuously. When a shortage affected one system, solutions were developed holistically rather than in isolation, ensuring that modifications in one area did not create downstream issues elsewhere. This integrated approach reduced complexity, shortened response times, and created a feedback loop where improvements in one domain informed enhancements across the entire ecosystem. And financial strength underpinned all of these capabilities. Investments in R&D, factory tooling, and software infrastructure provided the resources necessary to pivot quickly under pressure. While competitors cut back, the company leveraged its capital to accelerate redesigns, expand supplier engagement, and maintain production continuity. This countercyclical investment strategy not only mitigated the immediate impact of the chip shortage, but strengthened the operational foundation for future challenges. And the chip shortage also highlighted the importance of system-wide thinking. Vehicles were designed with centralized computing architectures that reduced the number of individual chips, required lowering overall exposure to scarcity. Modular software allowed features to be decoupled from specific hardware, ensuring that critical systems could continue operating while alternative components were tested and validated. By simplifying complexity and building adaptability into both hardware and software, the company turned a potential vulnerability into a structural advantage. And through this combination of forward-thinking design, software control, vertical integration, manufacturing flexibility, and a culture of rapid iteration, the company not only weathered the semiconductor crisis, but emerged with a stronger, more resilient ecosystem. Each challenge became an opportunity to validate design philosophy, enhance operational processes, and reinforce the principle that agility and control define leadership in the modern mobility landscape.